Okay. Thanks, Francesca. Thanks for the invitation, and hello, everyone. So for the person who doesn't not yet take the opportunity to, to know me, this is the Makhlouf Hadji from SystemX. So I'm going to speak about digital twins for networks of future. And I think the talk will, first of all, be based on some overview on what is this buzzword is, let's say, is meaning. I'm talking about digital twins, because everyone, I suppose that you are familiar with networks of future. So we will try to make some, let's say, clarifications, provide some definitions on how the networks of future will evolve with this new techno or this new paradigm, which is the digital twin. And I will, let's say, I will close this talk by opening some research challenges that have the merit to be addressed if you are interested. So the outline is a very classical one. So I will start by giving some definitions to make sure, to be sure that everyone has at least let's say, the essential meanings of the digital twin. And then after that, there is a very important topic in which a lot of researchers actually, they are working on it, which is how to define, how to design a reference architecture of a digital twin in a manner which will be totally agnostic to the different use cases. And then we will see that when we select a use case, this reference architecture could be somehow, needs somehow to be, let's say, customized to fit within the expectations or within the needs of this use case. And we also will address an important topic, which will also, let's say, will address the open source tools for digital twins, because I'm just focusing on open source because I think this is most important for us as researchers, at least, to see that there are some open source tools, there are some open source solutions to deploy easily digital twins if you want to make, some test beds without a lot of problems. But yeah, for your information, of course, there are a lot of solutions which are not free, and they are actually solutions made to, let's say, to cover some needs, some special use cases, and then maybe we can just address some of them. I will finalize my presentation by, let's say, just recalling some important domains of applications in which actually we can observe that the digital twin is really gaining more space every day. And of course, I will make the focus on how the digital twins are actually changing somehow the evolution of networks of future, or the inverse also, how the networks of future will also interact with the digital twins to maybe improve the performance or at least reduce the costs. This is the plan of the outline of my presentation. Now, if I am going to, let's say, introduce the digital twin, so I am going to start with a well-known definition since 2010, which is actually provided by NASA, and which is more focusing on, let's say, independent vehicle systems, let's say it this way. I'm highlighting some keywords to attract your attention on them, because when we would like to talk about digital twins, so let's say necessary, we suppose that we have physical assets or physical, let's say, cyber physical systems, okay? So we need to make the twinning of these physical assets using a lot of techniques, a lot of tools to virtualize somehow the different functionalities of the physical system, but also the environment in which this physical system is evolving. So this is a complicated, it will depend, of course, on the selected physical system to try to, let's say, virtualize somehow. And if we can take a look to the definition of provided one of the first definitions of NASA, so we can see here the keywords which are represented by physical models, and the physical models will be necessary to represent how the components of the physical system are evolving during time. We have also another important keyword which is used, which is actually represented by the sensor updates, which means that we need to put some sensors to collect data, and we need to make some updates and reconfigurations and actuations through these sensors to different objectives that will be addressed later. And the last keyword I highlighted here in this NASA definition is to mirror the life of its flying terrain, which means that we need to try to build a twin which is ideally 100% perfect and which can represent 100% the physical model in a perfect world, of course. That's the, let's say, the objectives we would like to reach if we would like to talk about a digital twin of a physical asset. This definition is actually has evolved a lot of during time. In the right side of this slide, you can just find, at least in 2017, so let's say recently, 17 definitions totally different somehow when they describe what is a digital twin, right? In 2019, we can find in the literature, so 46 definitions. And after 2019, nowadays, we can find more than 120 definitions. Some of them, they are totally different, but almost of them, at least they contain one keyword to make that the different definitions converging somehow to one objective. And this is due to the fact that the use cases, the different studied, considered, let's say, several physical systems, so just physical assets, they are totally different. And this means that the definitions, let's say the twinning of these physical assets made the definitions completely different. That's why we can actually have more than 100 definitions of the digital twin. I am also, again, trying to throw different references here. I am highlighting again the keywords of the different definitions used in the literature of the digital twin, and through these definitions, which are somehow recent, we can find very interesting keywords to specify more and to try to understand more what could be a digital twin of a physical system. So in reference one, and all of these references are actually provided at the end of the presentation. So we can find some keywords such as cloud platform and simulate the health condition. These are very interesting keywords saying that if we would like to, let's say, to provide a twin or digital twin of a physical twin or a physical asset, because we would like to make some, let's say, to assess its health every second or every 1 hour or every day. It depends on the different use cases. And this is, let's say, in the literature, when you take a look to the literature, so this is one of things which are really the most cited thing, which consists to say, what is this, the health of my physical system? Is it going to be broken in 1 month or in 1 hour? And these are topics which are very close to what we call actually the maintenance, or specifically the predictive maintenance, right? And if we can also go through the first definition, we can find other, let's say, keywords which makes the digital twin more important and specifically totally different to what we we have today in terms of simulations. It's really more than simulation models actually. We have new thing actually, because as we can have data, so we call here, we talk here about data-driven analytical algorithms. So we collect the data thanks to the digital twin, and then try to make this analytics. It will depend if we are in use cases dealing with real-time scenarios or not, but at least we have this, what we call here, the data-driven analytical algorithms. So the new algorithms that will be, let's say, provided within the digital twins, they will no more use, let's say, theoretical hypotheses, for example, but they will be based on what we call here in the data and the information which is actually in the data to be investigated, and then maybe coupled to the simulations, to the optimizations, to the analytics in terms of machine learning, for example, etc. And the other, the last one, actually the last keyword in this first definition is about to get physical knowledge. Using the digital twin, we can just investigate the data and try to understand what is actually what could be extracted in terms of information on the physical system. And this knowledge is very important to make your models more accurate and take the decision more accurate and more rational. And also this information, this knowledge on the physical system could be also later shared to other digital twins. And then we will talk about the interoperability between the digital twins. Okay. I'm not going to, let's say, to address all of these keywords, all of these definitions, but to say that a lot of definitions with very important keywords that we have maybe to retain, and they make the definition and the role of the digital twin for sure larger, but very, very relevant. As we said, one of the first, let's say, keywords that can be rapidly extracted from the definition of digital twin is the fatigue damage, for example, of the physical asset, for example. So we will use this digital twin to assess the health of a physical asset. One of the let's say parameter that which makes the construction of a digital twin difficult or complex is this factor, the high fidelity model to construct your digital twin. It is often, at least nowadays, very complicated to represent 100% exactly what would you have in your physical asset in terms of digital twin. So and so on. You can have some very interesting things here. For example, probabilistic simulation. You have also how to collect the data, the input data and the quality of your data, but also how to manage with the uncertainties when you collect this data, etc. This picture is summarizing all of what actually what I'm saying, and you can find it, of course. Everything here is not my own prediction, but this is really an overview on what is existing actually in the literature. So these informations are totally free and they are available in different papers. So we start here the definition before conversion to this one. We start by the digital model, and this figure is actually trying to show the difference between simulations, optimizations to, what we did until now, and what will be the future using this digital twin. So in the left side of the picture, we have, we can see that we have a physical thing, we have a physical object, and then we will try to make its digital replica or its digital twin. But we are not going to talk about digital twin in this case. This dashed line is actually represented here to say that the communications, they are offline. Okay, so that's exactly what we talk about the digital model. So we have a physical thing, and from time to time, I'm going to make some communications, input data, etc., to try to see how this digital replica will consume this data and then make the feedback in offline. And other definition, let's say, we consider that the communication from the physical thing to the digital replica are in real time, okay? But the feedback is not necessarily in real time. That is something which can made in offline, for example. So that's what we call here the digital shadow. And what is actually interesting for us is the digital twin. And the digital twin definition, according to this representation, is that everything is in real time, okay? So this is just, for your attention, it's just a point of view of, let's say, of publication that you can find at the end of the presentation. But of course, there are a lot of definitions making the digital twin definition larger than what is actually very, let's say, simplified a lot in this representation. And there is another thing which is totally new, which is the digital twin predictive, using digital replica in including the cybersecurity aspects here. So these are different schemas. Really, let's say it's just a big picture, but the details are really on these different boxes and also in the different rows linking the two boxes. Okay. I will come back to provide more details on this. Why actually are we addressing digital twins?
Sorry, Makhlouf.
Yes.
We have a question from the room.
I cannot see them. I cannot see them, please. So
I will repeat the question for you because we don't have a mic. Just 1 second.
Yeah.
So what is the difference between the last two pictures?
Yeah.
The right nose.
Yeah, the difference.
The difference between the two right nose pictures.
Yeah, the difference between the digital twin and the digital twin predictive. What is the difference exactly between these two?
Yeah, according to this this reference, the reference providing this picture is that in the right side of this picture, I mean the digital twin predictive, I think there is a new thing here, which is including cyber security aspects. I don't have the details on how to integrate this within the digital replica to provide what they call here digital twin predictive. But at least they added something new, and I think this is about how to add this cyber security from end to end in the digital part. Hopefully, this is the difference, if I understand correctly, if I remember correctly, what is provided in this reference.
Okay, thank you very much.
No problem. Everyone now is trying to understand what could be the benefits of the digital twin and compare it to the, let's say, to the situation as it is before using the digital twin. So this slide is just summarizing some opportunities and some benefits, and this is also what is extracted from the literature. So the first one is this digital twin will allow us to test different designs and scenarios without the risk of damaging equipment. I think this is a trivial point. This is an obvious one because, of course, if you would like to let's say, to modify the communications, to modify, let's say, the link, virtually speaking, of course, in your digital twin, so you can do everything you want. And there is no risk, of course, if you are not, of course, you are not making the reconfiguration, the feedback to the physical asset. So you can do what you want because everything is virtual, right? Reuse of created knowledge. This is exactly what I was mentioning before, because when you will use the digital network, digital twin, sorry, so you can get new information, and this knowledge, this information will be also reusable for other, let's say, other projects or other digital twins representing different assets, and then make this interoperability exploiting or investigating the how to use this knowledge to improve the performance or at least to improve in terms of the data, for example, the information they could exploit or they could use. And the last one is to enable the use of big data for monitoring, optimization, diagnostic, and prognostics. That's exactly what we call actually the services that could be provided by your digital twin. For example, collecting or streaming data from the physical, let's say, asset. This could be, let's say, easy to use within the digital twin, easy, of course, between brackets, to use for monitoring, but also for services such as optimization. I will come back especially on this point to, let's say, to make a focus on the for the network of future, but also to make the diagnostic and prognostic purposes in the era of digital twin, because they are, let's say, they are exploiting or using the data collected by this digital twin, analyzing them, and then try to understand what's going on in terms of diagnostic, for example, or prognostic, and then make the feedback to the digital twin, to the digital, to the physical asset, sorry, for actions or for actuation. So the question of, is there a reference architecture of the digital twin? So what we did here is of course, let's say we opened some papers and also some specific papers addressing the architecture. Is there a reference architecture for different domains? So the response is, the question is very hard actually, and we find some, let's say, a paper addressing the reference architecture of a digital twin using microservices. I'm not going to be forced to address all of these details one by one because they are, it's very dense actually. But what we understand here is the reference architecture based on microservices is something which we can fit in what is actually provided in a technical document provided by ISO 23247. So this document is addressing a reference architecture totally agnostic of the digital twin, totally agnostic on the different use cases. So here we can find, let's say, a decomposition of this reference architecture using microservices. So we can find a lot of services that we can, for example, use, especially for the cybersecurity, for example, data analytics services, etc., which can, let's say, ensure and guarantee the streaming of the data, etc., etc. And of course, when we talk about microservices also, so we can find, let's say, orchestrations within and management components within this architecture. And this could be totally agnostic to different use cases because we would like to, let's say, get some answers to the question, is there any reference architecture of a digital twin that could be totally agnostic to different use cases? In terms of, is there any tools or open source tools, especially for digital twins? So we also find something that could be interesting, but maybe before going to provide different, let's say, open source tools, this picture also is summarizing the different existing tools for digital twin in terms of, for example, tools for digital twin services. So I was talking about the optimization a few minutes before, and the tools also that can make the predictive maintenance to say, for example, to understand or to predict when the link, for example, of your network is going to be broken, or when the server is going to be in a failure mode, etc., etc. We have also tools for digital twin modeling, because we think the digital twin, we will embed a lot of, let's say, models to try to finally to make decision aid, accurate decision aid according to, let's say, the models using the data, the models using the physical representation or modeling or constraints, but also what is actually let's say, is expected. We are talking about the hybridation of these two models, the physical one and the data-driven one, to try to once again to improve the accuracy of the decision that we have to make as a feedback to the physical asset. So we have a lot of let's say lot of tools here which are summarized. I don't have all of the let's say explanations of some of them, but at least we need to understand how the physical system is done, what are or how are the flows within the physical system, and in which environment is the physical system evolving during time. We have also tools for connections between the physical and the digital, let's say, twin. We have tools for the physical world to represent as we can what is going on within the physical. And we have tools for digital twin data in terms of data fusion, for example, or how to process. And also one of the most important challenges that I will also address later is about the data storage, for example, because if in some cases we need to collect in real time the data in a continuous way, so we need to find strategies to make data storage efficient in terms of the performance for our digital twin. What we find now, which is actually interesting, is the deployment using open source tools, which are actually provided by Eclipse. Okay, so we have components. This is actually a technological pipeline coming from the what is called here HONO, and which will be connected to what we call here DITO. But before, maybe just some explanations on HONO is actually making the let's say the deployment of and the connection of the physical devices here, IoT devices. Let's say this is a virtual representation of these devices, and it allows also to get the data collected from these devices. After that, we send the information to DITO, which is let's say actually it's a black box. Which is able to host the different services and the visualization also of what is going on in terms of performance or in terms of different KPIs you would like to see, to observe in your physical devices or in your physical system. And this one, D2, is actually also able to host new algorithm, new services such as maintenance, for example, optimization, etc. And then we will use classical tools such as Kafka, for example, and InfluxDB to manage with the storage of this data. And also some open tools actually, such as Grafana, for example, to make the visualization of the result and of the performance of your physical asset using your digital twin. I'm not expert here in these different technologies, but we try to build this pipeline actually, and we got something which is working fine actually. But yeah, not obvious for sure, but at least we are sure that it can work if we add some data, some technical data. And in parallel to this open source, what is not actually mentioned in this presentation, yeah, it's important to know that there are a lot of solutions which are not totally open, using digital twins, for example, to represent the connected health of a given person, for example. So they are solutions which are totally available, but of course they are not free. So a lot of solutions also, for example, in the domain of predictive maintenance, which are provided by General Electric, I think, which are also some, let's say, non-open solutions for it. I'm using just this picture to represent what we call here the 5-dimension model of the digital twin. And these dimensions are actually constituted by the physical domain, the virtual one, the data collected from the physical domain or physical asset, the different services, and of course the different communications between the digital and the physical asset here. That's what we call here in this reference, the 5D digital twin representation. And we can find different sectors which are actually relying on the usage of digital twin for different purposes, for different objectives, such as, for example, gaining in times, reducing the costs, for example, in different domains. We have the automobile, we have the aerospace, the healthcare, the smart city, smart building, manufacturing, the vessel, and drilling platform, electricity, etc. In SystemX, if you allow me, we are at least this use case, electricity. We also are the smart city use case. We have also the smart vessel use case and the manufacturing, of course, use cases, which are actually going to be addressed in our program, which we call here Digital Twin for Industries. Now let's make a focus after these different definitions and different details on how the digital twin is working, and let's make a quick focus on what could be a digital twin for networks. And I think this is the part you are let's say more interested in this presentation. So I am starting it by giving some details in terms of motivation. So I'm saying that novel network applications with complex requirements cannot be met using traditional network management solutions. So we need, for example, these kind of technologies which are actually relying on ultra low deterministic latency, such as, for example, AR/VR. And also we can also rely on the usage of one use case, as I mentioned it before, is the vehicular networks with real-time constraints. So we can just use this virtual representation to, let's say, to reduce the cost when managing, when modifying the network, trying to understand what's going on if I move this node to another one, or try to reconfigure the network as I want. Of course, without impacting the physical, let's say, representation of this twin. And also the interaction with digital twin for networks does not require access to the real network. Exactly what I am saying. I mean, we can just play with the digital representation to understand what could be the impact on the real network. So behind these motivations, we will try to, I'm using a very recent paper to try to explain how it could be the digital twin for networks made, especially in terms of architecture, but also we will see some services. If you consider the picture on the right side of the presentation, so we can see that we have network infrastructure. Okay, so we can get physical links and physical nodes. And we have also what we call here the network configuration. Actually, the network configuration here could be also integrated to the digital representation. And this is what we call here the digital twin of our network configuration. So we have different components to constitute a digital twin. First of all, we need to simulate or let's say represent the different components of my network here. Let's say this is my network here, from the box to in the left to the box in the right. And we can use some data models, let's say, for example, some intelligence based on EI, for example, machine learning models, to assess or to analyze what's going on in my network in terms of failures, but also in terms of different services, for example, rerouting the traffic or scheduling a new task or deploying a new service, etc. And the different applications here that could be integrated within the digital representation in terms of management, as it is actually mentioned in the microservice architecture. So we can add services as we want. So here, for example, we mentioned four examples, or in terms of services: network planning, the optimization, the troubleshooting, and the what if, in terms of if I move, let's say, or if I'm going to break, for example, a link, what could be the impact on my physical network? That's the different services. And of course, the most important thing in digital twin, not in digital shadow, is this feedback. I mean, when I I am analyzing my the data coming from the digital from the physical network, and I am coupling it somehow to simulations. I am coupling it somehow to physical models, physical representation of my network, of my substrate network, and also my using this also coupling with the optimization if necessary. So I am going to give a decision to my physical network here, what we call here in the red color by the feedback. This is what is characterizing the digital twin compared to, let's say, classical models, for example, the simulation or just the analysis using data. And this feedback will, let's say, will address a decision to the person managing this network infrastructure to take the decision. So here we can just see, for example, the using different metrics. That's this kind of metrics could be used in terms of decision or in terms of the feedback that we would like to, let's say, to actuate on the network infrastructure. In this slide, we are more focusing on the network optimization because I like a lot this kind of topic. So how this network optimization could evolve with digital twins. So here we are mentioning some examples, and in the left side of the slide is giving some, let's say, some steps to show how this network optimization could be used within the digital twin. So imagine that we have network infrastructure, which is actually provided here, and we have its digital twin. So we need to build or to provide services in the digital twin, which are actually these kind of services, network optimizer, using different techniques or different models, existing models, but also the models you can provide yourself as a service. So imagine that we have this network intent. I need to do something. I need to analyze the traffic in my network. I need to, let's say, deploy requests in my substrate network using the digital twin, for example. Or here, what is actually discussed is network configuration, for example, the routing. So this kind of services are asking the digital twin according to the status, the current status at time t, in terms of what is this status of the physical infrastructure, especially using some metrics for the routing. I am targeting the routing in the on the physical network. So I am using these optimization services. I can, let's say, in near real time, I'm not sure that we can do this in real time, but in near real time, we can just make algorithms that converge very quickly to give us this network performance and the new routing we would like to let's say, to see or to apply for this request. And then we will make this feedback to apply therefore as a new reconfiguration or as a new routing solution in the physical infrastructure. And then we make the loop in terms of updating. Now, if I am accepting this request and then I am rerouting the traffic according to this optimized solution, then I will update my data if I am streaming the data in near real time or in real time, to see that in the digital twin, we now have some updates on the physical infrastructure and so on. So these different 5 steps is making the loop between the physical asset and the digital twin representation of this network infrastructure for a simple example, which is the routing of traffic. Finalizing now, finally, I'm just opening some research challenges that these are not mine, of course. That's exactly what we can find in the literature. The first one is the data collection and the storage. We, as I mentioned before, a good digital twin is a digital twin which is able to provide you a good decision or good, let's say, rational decision to make as a feedback to your physical asset. That's why this decision is actually based on different models, on the hybridation of different models, the physical one, the data-driven one, the simulations, and different kind of services such as optimization. Coupling or merging all of these services to finally build a rational decision is actually based, of course, for some of them on the quality of the data, of course, you are consuming from the physical asset. So data collection techniques, such as, of course, as this data is collected from different sources, makes building the accurate models very, let's say, very complicated. And the other thing is the storage, as I said before, storing this data within this digital twin somewhere to be consumed from time to time, or to be consumed in near real time. So this is an open challenge to design specific solutions for the storage of the data to be used easily by the different services of your digital twin. Another important point is that we know that when we collect the data, some of points of this data is totally missing, and some of them, because of different aspects, let's say, for example, the sensors, they are not in nominal, let's say, situations. So we do have some uncertainties when we collect this data. So we need to provide to network operators, if we are in this topic of digital twin for networks, so we need to provide robust solutions using dealing with this uncertainty in the digital twin part. So this could be, for example, using stochastic optimization or a different kind of methods that can deal with the uncertainty in the digital part, digital twin part. And also, as I said, representing of physical, cyber physical assets using digital twins is very complicated, especially for complex systems. Because we need to represent the shape of your system, but also all of the different interconnections, and which is actually what we call here representation with a fine-grained representation, actually, to represent very well different interconnections. And this is very complicated to build finally 100% high fidelity score of the representation of the physical asset. So this is also something that could be investigated to improve the quality or the decision that could be provided by the digital twin. I think I'm done. I am providing here in this slide the different let's say references. Just for the last, or the paper which is actually addressing the digital twin for networks, you can find just the reference, which is the 6th reference. The other references, they are giving more details on the definitions, but also the added values of these digital twins and the different domains in which they could be applied. I am done definitely with this.
Thank you very much.
Are there any questions?
So yeah, I'll ask you. We have questions in the room, so I listen to them and I repeat them to you.
Thank you, Francesca.
Yes, it's about the first example, the aircraft or whatever, right? So with the digital twin, where you will have this feedback control, and you would have just propagation delay there. And so I wonder whether this, the control of system with delay leads to possible oscillations,
yeah,
and lack of controllability for just the linear system theory. So, I mean, does one know the type of problems, yeah, where this approach lies?
Yeah.
And the case where you should not apply that because of impossible oscillation or misbehavior of control with delay?
Yeah, perfect. So I will relate the question and I will add a piece of my own. So the problem is about the feedback loop that you have from the digital twin to the physical world. So I guess you can go back to the very first definition from NASA. And the question is, if you have a physical system like the one that is concerned in this definition, you will have constraints on having the feedback with the latency, which is compatible with the functioning of the physical component. So are these problems already tackled in the literature? So can you, for example, say when you would be able to use this kind of feedback in real time for operating for operating your physical system?
Yeah, I got the question. Thank you, and thanks for asking this point. Yes, we found some literature papers addressing this point in terms of the feedback. Is it actually considered in real time? And if this is the case, which kind of, let's say, communication technologies are we going to use? But it's actually a little bit complex point, because how it is actually addressed in the literature, it is really based by the point of view of the use cases. So some use cases, they are not asking for making this feedback in real time. So, I mean, the question is not actually no more available for this use case. There are other use cases, the feedback is done from time to time in terms of on demand. So when I want to make this feedback, so I will do it. And there is, of course, the most hampering point is actually this real-time feedback to the system. So we didn't investigate this point deeply, but for sure there are some papers addressing at the same time the communication part of, let's say, the different communication technologies that should be or could be used to ensure this near real-time feedback. But also at the same time, this, the usage of this new paradigm using the edge computing, etc., especially to store the data where it is necessary to be stored, to be consumed in real time also by the digital twin. But I cannot give more details because I didn't take time to read them seriously, let's say.
So I have another piece that plugs to this question. And okay, I have the impression that most of the time, the feedback that is given from the digital twin is an informative feedback and not really like an actuation like you would find in a cyber physical system, if you see what I mean.
Yeah.
Okay.
So your question is?
So my question is, do you need?
Is it just an information to your physical system, and it's up to the physical system to take this information into account
and decide on?
Yeah. No, actually the feedback is really an actuation, not all of the time for sure. But if you consider where the domain in which the digital twin is actually almost used is the predictive maintenance. For example, when you study, when you, let's say, analyze the health of your physical system, and then you, especially in the domain of predictive maintenance, so you see that, you know that in, let's say, in 10 hours, your server is going to be down, or the link between two nodes is actually going to be in a failure, or is actually totally damaged somehow. So you have this information, and then you need to actuate really, for example, if we use the example of the routing, so you need to update thanks to this information coming from the streaming of the data, to see that there is no more, let's say, a road from this one to this one through this one, for example, you see, because somehow this link, for example, is totally damaged. So this reconfiguration could be done within the digital part, okay? And then the actuation would be used to the physical substrate, saying that this route is actually totally offline, and then we need to reroute the traffic somehow, okay? So in this digital representation, as I mentioned it in the microservices, there are a lot of managers, a lot of services that we can fit within this digital part to manage the physical network, but in terms of actuation, the feedback, but also in terms of analyzing without impacting what is going on in the physical substrate. So for the predictive maintenance use case, as I mentioned it, it is very useful to do this here in real time and to take the decision to actuate on the physical network according to this example.
Okay, thank you. Any other questions?
So, yeah, the global question about the, since it doesn't apply to real time, I mean, you can't fly a plane or do something of this type on the twin on the ground, right? Doesn't make sense. Due to the this latency questions and so, I mean, is there like I mean, what is the typical situation where you would have this feedback control and where the thing still makes sense? So is there like a class of applications which clearly will not contain vehicle
real time
distant driving or flying an airplane from the ground? So what is the class of application where this feedback is still applicable despite the latency? And the lack of reliability of wireless links.
I'm not sure to get everything, Francesco.
I'm going to repeat. So the question is always about the feedback loop. So this feedback loop for lack of decision and actuation and for technical problems on the radio connection itself, we all agree it's not going to use to fly your plane with a decision taken in the digital twin. So the question is, what are the classes of problems that are that can be solved using this digital twin? Besides like operating in real time in a time critical way your physical assets.
If I understand correctly the question, in network domain, so if we are not able to guarantee this feedback in real time, we are for sure we have the information that we need to reconfigure the network according to the decision made by these services in the digital twin. So if we are not able to make the decision in time or in real time, so yeah, maybe some problems will occur for sure in the physical infrastructure. But I'm not sure understanding well the question. In other domains, as I said, the feedback is not necessary in real time, but it will depend on the different use cases, as I said. Please complete my understanding if I am wrong, actually, please.
Yeah, so I guess the class is maintenance, and I think maybe the important thing is that you can feed, you have the real-time input of data from your system, so your decision is based on the present state of the system, which would not be if you couldn't source data in real time from the system. I guess.
Yes.
And I have a very final one.
Yeah, go ahead.
So in all representations that we saw here, you are using machine learning or neural networks to represent the model. So do you think this is a mandatory requirement to call this thing a digital twin, or do you have digital twins which are like physics modeling based, and that's it?
Okay. Generally speaking, we in the digital twin, the new thing is that we have this data collected from the physical substrate, right? Let's say, for example, for a physical network. And this data is, as I said, need to be, let's say, consumed somehow using models, right? That's what we call here the data-driven models. So within the digital twins, we need to build different types of models. So data-driven models, especially using AI, preferably, I mean, and simulations also, but also the physical models in terms of if I have some knowledge on how to model, let's say, the remaining useful life, for example, let's say for or link or server. So this kind of physical model, physical representation could be also addressed here. And what is actually a la mode is the hybridation of all of these models to make the decision better, because some researchers, they have seen that data-driven models, they are good, but they are missing some information, or they are actually suffering from somehow the accuracy. Other researchers, they are really pushing the physical models, but the problem of the physical models is that they are very time consuming. And if when you are in near real-time situations, so you need quick decisions, and the physical models, they are not helping in this sense. And then the new thing is how to hybrid these kind of models to improve the solution, improve the decision that could be after that made as a feedback to your physical asset. So as we are collecting data, I am not saying that machine learning or deep learning, or it will depend on the situation you are considering to analyze your data. Feel free to, of course, to investigate different solutions. But the most important is to build good models that could be ideally in a hybrid way to improve the feedback and the quality of the feedback to finally manage correctly and in a cost-efficient way your physical asset or your physical substrate here.
Okay, so I have another small one.
Yeah.
I get why we want to have machine learning inside of the digital twin, but then the question becomes, do you have a single model for the physical object or a collection of models to deliver different services? Because now the problem for me is, it seems to me that is a very hard feat to train the thing, and I don't know how you could get guarantees or to be reassured that the model that you are using actually spits out the correct.
Yeah, what is not, I got your question. What is not actually mentioned in this kind of representation is really a very important part. I talked about the storage of the data, but also which is a parallel, let's say, topic is where to deploy these resources for the computation, right? And how they could be related and link it to the digital twin, because the digital twin will run different models, but we have to be, let's say, aware that somewhere we have to provide these resources in terms of CPU, GPU, or something else to get the decision in acceptable times, let's say, okay? So this is actually missing in this representation, and I do agree that we didn't find a lot of papers looking to this part, because they are actually a lot of researchers, they are focusing on what could be the different components of the digital twin. They don't care a lot on terms of the technology of communications between the physical, in terms of feedback, but also in terms of collecting the data. They don't care a lot on where to store the data, especially in the cases in where we are going to stream the data in real time. So we at a given time we will get hot data, and also at another given time, so we can get cold data. So where to store them, but also to get this performance in terms of computation in acceptable time, we need to let's say design somehow an architecture of the digital twin in terms of the resources and the network of resources to be deployed in terms of computation to get this service of computation in acceptable time. This is not actually mentioned here, and I think this is an important point to that has the merit to be investigated.
Thank you very much. So are there other questions? I think we are good. Thank you very much, Makhlouf, for your talk. And so we wrap it up here. Have a good day.
All right. Thank you so much. Goodbye.
Bye.